Good morning, ladies and gentlemen, and maybe good afternoon for some people from Indonesia, my college. Thank you for inviting me to the organizing committee that's allowed me to talk about this presentation, especially for you, Michael, for allow me to talk in this conference. For the audience, welcome and nice to meet you in this workshop. I will present a talk entitled Modern Computer Vision for a Better Tomorrow. This is a more generic or general talks, not to detail. I'm Setiawan Hadi from Universitas Padjadjaran, Indonesia. Please enjoy my talk and I'm open to discuss. Let's begin. My presentation will be divided into 4 parts. In the first part, I will introduce vision and computer vision in general, including the history of computer vision. In the second part, I will present the current development of computer vision, including the main tasks and pipeline, and also implementation in industry and other areas. In the third part, I will talk about the future of computer vision based on the related technological development, such as cloud computing, high-speed GPU, CPU, and GPU, and also data availability. The last part, I will open the viewers to the benefit and advantages of using computer vision in daily life that can bring us a better living environment. Okay, I will introduce the vision and computer vision in general, including the history of computer vision in a short. Vision is a complex process. The human eye has many structures that contribute to the vision. Ciliary muscles change the shape of the lens to focus on both near and distant objects. The iris muscles control the size of the pupil depending on the lighting condition. The main refractive power in the eye comes from the cornea and the lens, which allows light to be focused on the retina. While opening your eyes and taking in your surroundings may seem like a simple task, your brain is working hard actually during this complex process that we call sight. For example, why it is more difficult to see in the dark and many other intricacies of how the brain helps us see. The process of vision requires that light entering the eye be captured by sensors that convert into neural signals that can be sent to the brain. These neuronal messages are processed to general mental visual representation of the world. Digital cameras and human eyes fulfill largely the same function. Images come in through a lens and are focused into a light-sensitive surface, which converts them into electrical impulses that can be processed by the brain or a computer respectively. There are some differences, however. Human eyes, it has fovea, a very sensitive area in the center of their field of vision. It is responsible for sharp central vision, also called foveal vision, which is necessary for humans for activities for which visual detail is primary importance, such as reading and driving. The retina consists of rod cells and cone cells. The rods are responsible for vision at low light levels or scotopic vision. Cones are responsible for vision at higher light levels or photopic vision, such as sensing the color red, green, and blue or RGB light. However, in digital cameras, they have uniform sensitivity to light across their whole field of vision. Light's intensity and color are picked up by RGB sensors, elements on a silicon chip, but they aren't as good as capturing a wide range of light levels as our eyes are. Typically, a modern digital camera can automatically tune its exposure to either bright or dark scenes, but it might lose some detail. For example, when it is tuned for dark exposure or any bright objects might just like white blobs. Human vision and machine vision systems both contains 2 basic components. The first is sensing device and the second is interpreting device. In this talk, I will focus on machine vision or computer vision. Before proceeding, let's see some historical timeline of computer vision. During the late 50s, 1950s, and early 1960s, computer vision was mostly limited to image analysis to mimic human vision systems and see how much a computer can resemble that. One of the first breakthroughs came during the 1950s. It was in the form of neural networks to detect the edges of an object in an image. This approach made it possible to sort simple shapes into categories such as circles and squares. Later, during 1970s, commercially deployed computer vision algorithms could interpret types of handwritten text using optical character recognition. In the 1990s and 2000, large datasets of human images were made available online for analysis, thereby providing an impetus for facial recognition research. Accuracy rates of computer vision algorithms have also gone up significantly, starting with a mere 50% accuracy for object identification and classification. The techniques used today have shown near 99% accuracy within just a span of few decades. In the next slide, we will see the comparison between computer vision in the past and current computer vision processing. Computer vision in the past is, we know, is a basic mechanism for computer vision are first extracting the meaningful features from the raw pixels, then matching these features to known labeled ones to achieve recognition. Then researcher has to do a lot of work, was manually inspection and selection of features. For example, PCA, Principal Component Analysis, was successfully applied to the first time to complex recognition problems, such as face classification. Another method appearing in the late 1990s, revolutionizing the domain, is called SIFT, Scale Invariant Feature Transform. But now, computer vision, we don't need to select the feature manually. Instead, the model can learn the feature from the image or the video, and it can process it and give output. Machine learning plays a crucial part in tackling image classification. Statistical ways were developed to discern images based on their features. SVMs, or support vector machines, were a long time the default solution for learning a mapping from complex structures to simple labels. The first convolutional neural networks, or CNN, was developed and applied to the recognition of characters with some success. The methods were computationally heavy or could not scale to grander problems. The computer vision community has adopted other machine learning algorithms over the years, including random forests, bag of words, Bayesian models, and neural networks. Now I will talk about the current development of computer vision, including the main tasks and pipeline, and also the implementation in industry and other areas. First, I will show you a picture. As humans, we can say that the picture is, however, it is not an easy task for the machine to describe what objects are in the picture. This is the foundation of why the computer vision field is hard to implement in the previous decade. But the purpose of computer vision is still the same, to get semantic information from images or videos. So, can you describe information about the image according to the arrow signs? Of course, I have already the answer. Well, how this image be processed by a machine and the machine shows information? This illustration brought us to generic definition of computer vision. So, computer vision is an interdisciplinary scientific field that deals with how computers can gain understanding what is being seen in digital images or videos. So the field of computer vision is changing rapidly at the moment because camera technology has been improving quickly over the last couple of decades. Not only is the resolution of cameras increasing, but they are also improving in other ways. They are more sensitive to low light conditions, have less noise, can operate in infrared, useful for detecting distances, and are getting very cheap. It's becoming reasonable to us to use multiple cameras, perhaps to give different angles or to get stereo vision. As mentioned before, vision systems basically are composed of two main components, sensing device and interpreting device. By sensing an image or a video, then processed by a machine, we hopefully get output that consists of information about the input or video. So, how the interpreting device works, in the next slide, I will show the pipeline of the computer vision process. Application of computer vision vary, but a typical vision systems use a similar sequence of distinct steps to process and analyze image data. These are referred as a vision pipeline. Many vision applications start off by acquiring images or data, then processing that data, performing some analysis and recognition steps, and finally making a prediction based on the extracted information. Before proceeding to the example implementation of this pipeline, let's apply above pipeline to an image classifier example. Let's apply the above pipeline to an image classifier example. Suppose we have an image of a motorcycle and we want to model the model to predict the probability of the object from the following classes, such as car, motorcycle, and dog. First, a computer receives visual input from an imaging device like a camera. This is typically captured as an image or sequence of images, forming a video. Each image is sent through some pre-processing steps whose purpose is to standardize each image. Common pre-processing steps such as grayscale, resizing, blurring, rotating, and many others are used for pre-processing tasks. Only by standardizing its image, for example, making them same size, can you then compare them and further analyze them in the same way. Next, we extract the feature or feature extraction. Features are what help us define certain object, and they are usually information about object shape or color. For example, some feature that distinguish the shape of a motorcycle, wheel, headlights, mudguard, and so on. The output of this process is a feature vector, which is a list of unique shapes that identify the object. Finally, these features are fed into a classification model. The step looks at the features vector from the previous step and predict the class of the image. Pretend that you are the classifier model, and let's go through the classification process. You look at the list of features in the vector feature one by one and try to define what is in the image. First, you see a feature of a wheel. Could this be a car, motorcycle, or a dog? Clearly, it isn't a dog because dogs don't have wheels, at least normal dogs, not robots. Then this could be an image of a car or a motorcycle. Then you move into the next feature, the headlights. It's a higher probability that this is a motorcycle than a usual car. The object has only two. The next feature is the rear mudguard. Again, there's a higher probability it is motorcycle. The object has only two wheels. This is closer to a motorcycle. And you keep going through all the features like the body, shape, pedal, etc. until you have created a better guess of the object in the image. So, this slide shows the computer vision tasks. taken from Fei Fei Li, Justin Johnson, and Serena Young's lecture 2017. Image segmentation is a processing technique that helps us separate an image into multiple parts called image objects, which can help us analyze the picture more simply. This picture shows the difference between object detection, semantic, and instant segmentation visually. Image segmentation is different from object detection and image recognition. Image segmentation returns granular information about the contents of an image. Object detection, which localizes objects in an image by drawing a bounding box. Image recognition assigns multiple labels to an entire image. Semantic segmentation is a problem of a computer vision in which our task is to assign a class to each pixel in the image using that image as input. In the case semantic segmentation, we don't care if we have multiple instances such as objects of the same class. We simply label them all with their class. So the modern computer vision, we are going to talk about it. With a modern advancement in artificial intelligence and computational power, computer vision has become an integral part of everyday life. Before going on, let's take a look at something else. Computer vision is a big subset of artificial intelligence, which encapsulates a lot of different fields such as robotics, machine learning, which is also data science in a way than deep learning. Convolutional neural networks are a big part of computer vision. Modern computer vision uses machine learning algorithms, more specifically a neural network, to determine insights from this data. These neural networks extract patterns from samples, working similar to human brains. Computers' ability to see and interpret the world around them helps in the analysis of the massive amounts of data created in daily operation. While traditional computer vision focuses on finding features manually, modern computer vision applied statistics and probability for finding features automatically. Now I will explain some technology that becomes foundation of modern computer vision. ImageNet, CNN, AlexNet, and GAN, or General Adversability Neural Network. Okay, until 2005, we did not have a lot of data to create these algorithms or to tell them if they are working well. But in 2009, everything changed, as many US institutions and industry players came together to create a massive dataset called ImageNet. The dataset included close to thousands object classes, including airplane, automobile, bird, cat, deer, dog, frog, and so on. With this, the problem was solved. We had a massive dataset to identify whether the model is working or not. Citing the ImageNet Kaggle challenge, the error rate in the ImageNet challenge has reduced significantly over the years, thanks to the introduction of models like AlexNet, which reduced the error rate by 16% in 2012, followed by Zeller and Fergus for 12%, Visual Geometry Group or VGG for 7.3%, and others. So the error rate is decreasing. So in 2012 onwards, people started using convolutional neural networks or CNNs and did some adjustment that reduced the error significantly. Before this, people relied on shallow neural networks where the error rate was close to 3%. CNN is the foundation for modern computer vision. Generally, it consists of input layer, convolutional layer, pooling layer, fully connected layer, softmax, logistic layer, and output layer. This picture illustrates small processes involved in CNN. I think you have already known about these pictures. AlexNet was one of the first key models to become popular in computer vision. To explain the science behind AlexNet from the basics, it is essential to know two key concepts: convolutional neural network and pooling on an image. The fundamental concept here is that you have filter which is similar than the size, which is smaller than the size of the image, and you slide the filter across the image at every point of time across the pixel. That creates an output of the convolution. Once you have convolution, you can use multiple filters to create multiple outputs. AlexNet contains close to 8 layers of convolution and pooling filters, as shown below. 5 convolution layers and 3 fully connected layers, which help identify the objects. On the other hand, a model like ResNet has about 152 layers to successfully identify or make sense of the object. GAN, or Generative Adversarial Network, is a class of machine learning framework, also popular application of computer vision. Designed by Ian Goodfellow and his colleagues in 2014, compared to neural networks like ResNet or AlexNet, which try to understand the image, GAN creates an image that doesn't exist. Two different neural networks are working here. They are working against each other. One network consists of real images, while the other consists of fake images created by the generator model. It includes a discriminator, which learns from the real image and compares the real image with fake images. Once you repeat this process several times, you can run multiple epoch, forward, backward, passes, etc. After a point of time, the generator starts creating really good images which look very realistic, and the discriminator can only be able to identify if the image is real or fake. One of the popular applications of GAN is deepfakes. Deepfakes are synthetic media in which a person in an existing video or image is replaced by someone else's likeness. Alexander Emini, on the left, and his colleagues at MIT and Harvard University have developed neural networks to model synthesized celebrities. This slide shows the deepfake video of former US President Barack Obama, which Emini unveiled at his introductory course on deep learning in 2020. The future of GANs look bright. There are several areas in which it can be used, particularly in creating infographics from the text, website designs, data compression, drug discovery, and development, generating text, music, art, and so on. So we have a question: what computer vision can do? You may be familiar with all these snapshots of Instagram filters. That is a form of computer vision because they are actually using your input image and then running a model over it to transform the image. You can see the different age of the person. We can change it using computer vision. Another thing is optical character recognition, which many of you would have seen if you have scanned document, and then it automatically can recognize the text in those documents. Lesson plate reading is another form of OCR, such as for self-driving cars. Self-driving cars, they are not in the marketplace yet. Although Tesla does have some that do like reverse parking and a bunch of highway cool stuff. Another computer vision can do is in sporting analysis. There are analysis of action called action recognition is one of computer vision can do. For example, in a football game, analysis of how a football player kicks a ball is an interesting activity that can be analyzed by computer vision. You probably would have seen some of these things that how football player act in football game. It also tracks the ball and tells you where it's going to end, including tracking the player. And last but not least, This is quite interesting. Until now, facial recognition is a way of identifying or conforming an individual identity using their face. Facial recognition systems can be used to identify people in photos, videos, or anything in real time. You would have actually seen and used a lot of things, as I mentioned before, but there is another application that computer vision can do in the military, in the manufacturing industry, in healthcare, also in automotive and driverless vehicles, and many more. So computer vision can see so we can see that computer vision applications are endless. So it makes the future of computer vision very bright. Computer vision is a rapidly growing field in research and applications. Advances in computer vision research are now more directly and immediately applicable to the commercial world. An increased need of automation and a growing demand for vision-guided robotics and other industry-specific systems are driving the massive adoption of computer vision application. In terms of financial things, the market is expected to grow from around 10.9 billion in 2019 to 17 billion by 2024. Students with skills in computer vision and machine vision are learning snapped up by companies even before they are close to graduation. So for computer vision, the present is bright, the present is bright and the future is even brighter. So computer vision in the future will perform a broader range of function. Not only computer vision technology be easier to train, but also be able to discern more from images than they do now. This also can be used in conjunction with other technologies or other subsets of AI to build more potent application. For instance, image captioning application can be combined with natural language generation to interpret the objects in the surroundings for visually challenged people. Computer vision will also play a vital role in the development of artificial generally intelligent or AGI and artificial super intelligent or SI by giving them ability to process information as well as or even better than the human visual system. Considering the capabilities of present-day computer vision, it might be hard to believe that there are more benefits and application of the technology that remains unexplored. The future computer vision will pave the way for artificial intelligence systems that are human as us. However, before doing so, there are few challenges that must be overcome, the biggest of them being the demystification of the black box of AI. That's because just like other deep learning application, computer vision, while being functionally effective, is undecipherable when it comes to its inner working. So the core technology of the future vision, the field of computer vision is rapidly transforming industries like automotive, healthcare, and robotics, and it can be difficult to stay up to date on the latest discoveries, trends, and advancement. The core technology that influencing and will continue to shape the future of computer vision development in 2022 and beyond are cloud computing, services that help scale deep learning solution. And then automated machine learning solution reduce the repetitive work required in standard machine learning pipeline. Next, transformer architectures developed by researchers to optimize computer vision tasks, and mobile devices incorporating computer vision technology. We'll see all these aspects. Cloud computing solution. Cloud computing provides data storage applications, servers, networks, and other computer system infrastructure to individuals or businesses over the internet. Cloud computing solutions offer quick, cost-effective, and scalable on-demand resources. Storage and high processing power are required for most machine learning solutions. The early phase development of dataset management often requires cloud computing resources for storage or access solution application like BigQuery, Hadoop, or Bigtail. GPU availability has accelerated computer vision solutions. However, GPUs alone aren't always enough to provide the scalability and uptime required by these applications, especially when servicing thousands or even millions of customers. Cloud computing provides the needed resources to start up and supplement existing on-premises infrastructure gaps. Cloud computing platforms including, Amazon Web Service, Google Cloud components of the machine learning and data science project pipeline, including data aggregation, model implementation, deployment, and monitoring. For computer vision developers, designing vision systems is important to be aware of these major cloud service providers' strengths and how they can be configured to meet specific and complex pipeline needs. Machine learning has achieved considerable success in recent years, and if ever-growing numbers of disciplines rely on it. However, this success crucially relies on human-machine learning experts to perform manual tasks. As complexity of these tasks is often beyond non-machine learning experts, the rapid growth of machine learning application has created a demand for off-the-shelf machine learning methods that can be used easily and without expert knowledge. It's called automatic machine learning. So AutoML will make machine learning more accessible, improve the efficiency of machine learning systems, accelerate research and AI application development. So this is what's called automatic machine learning. Deep learning methods have long been used to tackle computer vision challenges. Neural networks, architectures for face detection, lane detection, and pose estimation, for example, all use deep consecutive layers of CNN. New architecture for deep learning algorithm is emerging. It's called transformers. The transformer is a deep learning architecture introduced in Attention is All You Need paper. The paper methodology creates a computational representation of data by using attention mechanism to derive the significance of one part of the input data relative to other segments of the input data. Transformers have made a considerable impact with the NLP domain with generative pre-trained transformer called GPT and bidirectional encoder representation from transformer or BERT. The transformer does not use the convention of CNN, but research has shown the application of transformer models in vision-related tasks. There is a vision transformer, which is called, there is transformer for vision application, which is called vision transformer. So the vision transformers is a major breakthrough that emerged during the past year. It was the inclusion of new neural network topologies within computer vision. These new topologies have revolutionized the conventional way convolutional neural networks are used to solve typical computer vision tasks such as classification, object detection, and image segmentation. The eruption of transformers in the field of computer vision significantly improved the ability of these topologies to extract image features and thus improving the hit rate in the respective ImageNet benchmark. So now I will show you the nodes of computer vision in the future. We should validate computer vision model design. to ensure models work correctly with specific real-world application of computer vision. Organizations looking to adopt computer vision technology or enhance their current implementation should concentrate on the insights they want to gain. We can deliver better quality insights faster and at scale. We should focus on the specific outcomes they want to achieve. We should also monitor computer vision to ensure safety, reliability, privacy, and morality. Ethics framework can be a starting point to consider. So, we talk about modern living with computer vision. This is the last part of my talk. In the world today, generally speaking, people cannot live without technologies such as televisions, mobile phones, computers, and others. These technologies have slowly taken an essential part in people's day-to-day lives, and being without them would be unimaginable for some of us. As I previously described, computer vision technology is also part of our daily living, not only now, but also next in the future as part of modern daily livings. How computer vision can help us to a better tomorrow? The general sampling is the development of smart cities. A smart city uses information or communication technology to improve operational efficiency, share information with the public, and provide a better quality of government service and citizen welfare. The main goal of a smart city is to optimize city function and promote economic growth, with also improving the quality of life for citizens by using smart technologies and data analysis. The value lies in how this technology is used rather than how much technology is available. A city smartness is determined using a set of characteristics, including an infrastructure based on technology, environmental initiatives, practical and high. I'm sorry?
No, please.
Okay. Confident and progressive city plans. People are able to live and work within the city using its resources. The success of smart city relies on the relationship between the public and private sectors, as much of the work to create the maintain a data-driven environment falls outside the local government's remit. For example, smart surveillance cameras may need input and technology from several companies. So, computer vision, there are some implementation of computer vision for modern living. First is environment and energy. The use of machine learning in smart city makes it possible, above all, to control pollution by detecting, for example, CO2 emissions. Other air pollution prediction tools can inform authorities on decisions about reducing pollutant use. Sanitation and waste management, setting up an urban infrastructure made up of AI-powered robots allows a smart city to improve waste management. This ranges from sorting and recycling waste to cleaning the areas concerned, such as lakes, rivers, and so on. Transport. Some cities use a fleet of vehicles like buses or garbage trucks that can scan streets using camera and sensors. This makes it possible to create a 3D map of the city. This information can be used for maintenance, improvement, parking, and so on. Traffic. For traffic, the AI infrastructures in a smart city is mainly based on computer vision. This means the city is leveraging visual data to manage traffic. The simplest way is, for example, to place cameras in the city to identify areas of congestion in order to reduce traffic and accidents. Security. Another way to harness AI in smart cities is also through security. To do this, authorities use public data to identify criminals and monitor suspicious behavior. Suicide prevention in public spaces. Camera systems can also be used to implement suicide prevention system in public spaces by analyzing visual features like typical body language movement and recognizing unusual behavior. CCTV cameras with deep learning smart city applications can be used for assessing crisis behavior at suicide hotspots such as bus station. The main goal is the development of automated detection systems for early intervention that can potentially save lives. Smart water management. A smart world also includes the smart use of our most precious resource, water. In modern processing plants, not only water, but also large amounts of data are processed. Our smart water solution use this information and help improve water supply, disposal, and use. Connecting and evaluating different data enables safe and efficient monitoring and control of complex and critical information based on events. And finally, smart buildings. Self-optimization of buildings is part of smart city. Smart buildings are an important aspect of smart cities if they are intelligently networked and integrated into the overall concept. Building can contribute to the development of an efficient, stable, and profitable urban concept. So, computer vision for a better tomorrow. So what role of computer vision? Computer vision technology has become more widely available or making it more tempting to business in other areas.
Такую штуку там в кухне уронил на полу. Once again.
So computer vision technology has become more widely available. Computer vision is not just only about replacing human worker. In the 1950s, this question, if a machine could think like humans, now it become a reality. The big question is, will computer vision make human workers obsolete? In the field of medicine, computer vision is not just improving efficiency, it's saving lives. AI technology helping retailers improve customer service and create a personalized shopping experience. The agricultural industry has made a sharp shift toward high-tech, increasing all-round productivity by utilizing AI. Computer vision is now even surpassing human capabilities, increasing from 50% accuracy to 99% accuracy. So computer vision can perform tasks humans have not traditionally been able to. In the technical algorithm things, since the inception of modern computer vision methods, success in the application of these techniques could only be seen in the supervised domain. Human supervision use is necessary in order to make model useful for performing tasks such as image recognition, object detection, or semantic segmentation. However, new technology has revolutionized the paradigm of computer vision. In major shift, computer vision research has changed the focus of the field away from the guaranteed success with human supervision onto new frontiers, self-supervised and unsupervised learning. Today, computer vision is one of the major technological advances in our recent history. Combined with artificial intelligence and machine learning systems, computer vision is essential for companies that want to evolve into so-called Industry 4.0 into 5.0. What impact does this technological advance have on what will be the day-to-day life in our company? Several industries such as logistics, food, textiles, or automobiles currently use computer vision in many of their processes. For example, in the logistic and transport of raw materials, the use computer vision allows, among other things, the recognition of objects as well as control the verification of cargo transport and so on. So, computer vision.
Sechiban, we to have time for questions, we should try to.
Okay, I will end this presentation. Computer vision is one of the most widely adopted technologies. It is used at least 20% companies worldwide. Okay, I will come to the end of the presentation. Well, Computer vision is a technology we are facing today and tomorrow. As technology, it should make people happy. In terms of happiness, technology has made business much easier and faster. Technology makes it possible for sellers to exhibit much more products and services, contacting friends and family. Technology changed the educational system in various ways. Well, we come to the end of presentation. Sorry for passing the time limit. Thank you very much for your attention. Thank you.